Hello everybody. So we are going to do the calculations that we did last time for the velocity calculation. I mean the diameter calculation for turbulent flow using Microsoft Excel, and yeah, this is very similar to the file we used last time. So these are the three equations that we have, and again I did. I think, yeah, this table needs. I just deleted the numbers from the old table, so I'll update the columns one by one after we're done. So we start with assuming the friction factor, and then we calculate the diameter, and then Reynolds number, and then the friction factor. So we will put this as the diameter, and then let's add one more column here. So we'll have here Reynolds number and then F. So we'll just write the equations. So the first is the equal to 0.0759 times the friction factor, all power 0.2, and then Reynolds number is 27018.9 divided by the diameter. The friction factor can be calculated from this equation, so we'll assume any value, let's say 0.001 for example, and then the equation is 1 over square root of this friction factor plus 2 times log 2.51 divided by Reynolds number divided by square root of F. This is the equation. Of course, we can do the same trick, multiply it by big number to get high accuracy, and then this is the difference in F, which is the difference between the calculated and the assumed, and the percent difference is the difference divided by the calculated value. So this is what I'm going to do for all of them. And of course, this friction factor is not correct. So we need to go for the data ribbon, what if analysis, goal seek, and set this to 0 by changing the F, and this is the first try. So we got very big difference, very big difference in the friction factor. So again, as we did last time, we will put this as the calculated value, and we'll repeat this whole thing again and again. So now for the second trial, we will not do any new thing. All what we're going to do is to use goal seek to calculate the correct value of friction factor, and now the error or the difference decreased from 98% to 15%, which is very good. And if you compare this number and this number, the difference is getting closer. So we can do this one more time for the third trial. We want this to be 0 by changing the friction factor, and now the error is only 0.72%. So it's converging really quickly. And this one interesting thing about these kind of problems, that we can get the solution quickly here. We don't need to do many trials. For the last thing, or the last trial, this to the value of 0 by changing the friction factor, and the error is 0.03%. Okay, and if you check the friction factor, it's the change is this 2 and 8. This is the difference. The velocity is not exactly the same. It's 0.26. It's almost the same, but yeah, let's be kind of greedy here and try to do this for one more time, and then use goal seek to set this to 0 by changing the friction factor, and now the error is something, the difference is 10 power minus 7, and if you check these two numbers, they are almost identical. This is almost the same. So we're not going to get a lot of difference when we continue. So I think here the answer is very satisfactory, that this is the value of F, and this is the value of D. Of course, if you do this using the chart, I think it would be done at this point, because you cannot get the friction factor that accurate with the chart. Okay, the best thing you can do is the 178. So if you're super accurate, but and you see the difference between this value and this value is not that that significant. So it's fine. I mean, if you do this using the chart, it's going to be fine. So this is the solution if we use the three equations. Now let's go to the other option, which is combining all the equations together. So here I'm not going to use goal-seek here, and I did this last time, but I prefer to do this kind of manually. It's not manually, I mean to have it done in trials, and instead of using goal-seek to do the calculation for us. So I'm writing the equation, which is it's not for goal-seek, so I'm going to calculate this f from these two f's. So I'll take these two as the assumed values, and this is the calculated value. So I'm just calculating the left hand side of the equation. So it's -2 times log 2.51 times 0.0759 times f all power 0.2, and this is divided by 27018.9 divided by square root of f, and of course this is not f, this is 1 over square root f, so this needs to be raised to power -2, and this is no, it's not this. Anyway, so it should give kind of different calculated values, because it's not the same thing that we're doing before. So the difference in f is this minus this, and the error is the difference divided by the calculated value. And now we are going to just copy and paste. So here we are. We're almost getting the same thing. So after 3 trials, we got, or 4 trials, we got 0.017946, which is almost this. So I mean, if we like to continue, we can keep going as much as you want. So the error is getting to 10 power minus 13 now, and the point here is now we're done. We got the value. It's not changing that much, and the error is 0%. So this was after like 5 or 6 trials we got the final answer, but here it was done kind of quickly. So anyways, I mean these are 2 options. You're free to pick the one that you prefer, as long as you're doing it in the right way. And again, I repeat, if you're going to go with this option, you need to make sure that you write the equations properly, and you substitute correctly, so you don't mess with the equation, because only one equation, if something is wrong with it, you're done. And it's hard to track the error if you have any error here, which is not the case in this case. So if you have an error in one of the equations, there might be a possibility that you can track it. For instance, if you get a friction factor that is not logical above the range or below the range, then you can know that maybe the problem is in here or in Reynolds number that you used here. This is something that can help you track the error, while you cannot do this in the other way. And also there is one more point that is important here, which is let me just grab the presentation. That this is a very important point to keep in mind, that we were able to write this equation because the problem was a straightforward problem, meaning that when we dealt with the problem, we already knew the HL, the value of HL. But in this case, if you have a problem where there is you apply Bernoulli equation and you don't know the diameter, there might be some other velocities. I mean, you can have it in the term of u squared over 2g. So this will make the equation complicated, more complicated. The second is that you can have a case where the epsilon is not zero, and this is the common case. I mean, this was kind of simplified case that epsilon is zero. So if epsilon is not zero, the equation will be even more and more complicated. So you might have an equation that's not possible to combine in this shape. So this is a good option if you can do this. This is just something I wanted to refer to here, so that you know that this is not a solution that you can always apply. So yeah, I think this is all for this video, and I'll see you next video, inshallah. Goodbye.